right, so let's finish off Appendix D today on page A30. Page A30. A30 is graphs of trigonometric functions. So we want to look at the graphs of the 6 trig functions, starting with the graph of sine x. Okay, so when we're graphing any of our trig functions, we literally could make a table of values off of the values that we know from the unit circle and utilize those to sketch the graph. So that's the table that you see that I have here. I just went around and I pulled the values off of the unit circle that we know and gave the decimal version of them instead of, say, squared 3/2 version of them. And we could go through and plot those points. So let's say we start up here with 0, 0. So I've got the point 0, 0. And then pi over 6, 1/2. Now, this is pi over 2, so halfway between 0 and pi over 2 would be pi over 4, so a little bit in front of that would be pi over 6. So pi over 6, 1/2 would be about there. And then pi over 4, kind of halfway through, would be 0.7, so about there. And then pi over 3, a little bit past that, 0.87 would be about there, about 0.9. And then pi over 2, 1. And then if we connect those with a smooth curve, we would get the red curve that we see here. And so if we kept going with that same process, we know the values are all the same. They just change positive and negative. And so if we continued plotting those values, we would get that smooth continuous curve that you see there from 0 to 2 pi. We also know that the sine function is periodic, meaning it repeats itself every 2 pi, so that it would keep doing that same thing over and over and over again in both directions. So the practical way that we found for graphing this last year was just to pull 5 key points so that we could get the x-intercepts and so that we could get the extreme maximums and minimums. So we went through and we just pulled our quadrantal angles. So that was like 0, 0, pi over 2, 1, pi 0, 3 pi over 2, negative 1, and 2 pi 0. And so that gave us the basis for our graph. So what's the domain for your sine curve? What x values are we using here? What's your domain? Yeah, negative infinity to positive infinity, all real numbers, depending on which way they want it, interval notation or not. How about your range? What y values are we using? Negative 1 to 1, right? Brackets or parentheses in interval notation? Brackets, because we are equal to 1 and negative 1. Now, if you don't write this in interval notation, please be sure that you don't say negative 1 is less than or equal to x is less than or equal to 1. We just kind of get in the habit of that when we're writing interval notation or when we're writing our values. So this is actually easier if I write it in interval notation. I avoid using the wrong variable, but these are the y values for the range. And then remember, the period is how long it takes to repeat itself. So we've already said that it has a period of 2 pi, but that's because if you start at 0 and you go to where it starts repeating itself, that's right here. Pick any point that you want to. If I start right here and say, where does it start doing that same thing again? There it is, and that's 2 pi in between them. If I come down here and say, where does it start doing that same thing again? There it is, 2 pi in between them. Same thing if I go from here to here, or if I go from here to here. Pick any 2 points that you want where it starts repeating and look at the distance between them, and that will give you the period. Now, we could have the same type of discussion with the cosine curve. The 5 key points that we used for graphing the cosine curve were 0, 1, pi over 2, 0, pi negative 1, 3 pi over 2, 0, and 2 pi positive 1. And that gave us the basis for the cosine curve, and then we could extend it infinitely in both directions as well. So what's the domain for the cosine curve? All real numbers. What's my range? Yep, negative 1 to 1. And what's my period? 2 pi. It is the same, yes. Now, last year we talked about all of the different ways that we could modify this equation. So let's go back through that. We've already covered the idea of horizontal and vertical shifts in Appendix C when we were looking at our second degree equations. We said that any value subtracted from y is a vertical shift and any value subtracted from x is a horizontal shift. But there are several other things that we see here. If you have a number out in front of a function, it's going to change the amplitude. That's the highs and the lows. We saw that a little bit with our parabolas, like when you put a 2 out in front, it caused like a vertical stretch. stretch of a factor of 2. It's that same idea. Amplitude is just the highest value minus the lowest value divided by 2. It's how far up and how far down our curve is going. And that number out in front, if that A value is larger than 1, it causes a vertical stretch by that factor. If the A value is less than 1, between 0 and 1, it causes a vertical shrink by that factor. Amplitude is always positive, because when you put a negative out in front, then we start talking about reflection, right? So the amplitude is always a positive value. The other thing that we have is the B value. That B value causes a period change. And there were two different ways that we looked at that. Your new period would be your original period divided by your B value. So let's say that this was a 2 right here. What is the original period for sine? 2 pi. So if I divided that by my B value of 2, that would mean my new period is 1 pi. That means that I've got to be done drawing the sine curve by the time I get to 1 pi. So I'd have to smush that whole thing in there by the time I got to 1 pi. Another way that we talked about that was your B value was the number of complete cycles you had to put in the same amount of space you normally put 1. So again, if that B value is 2, you're saying I've got to put 2 of these in the same amount of space I normally put 1. So that would say, okay, I've got to have one of them done by the time I get here, and I got to have the second one done by the time I get here. So that same idea for the period. All right, so let's talk about tangent, cotangent, secant, and cosecant. We don't work as much with those as we do sine and cosine, but we do still need to know their graphs. Remember that tangent is the one that looks a little bit like the cubic function, only it's got some asymptotes. And cotangent, being its reciprocal, is easy for us to remember that it has the same kind of shape. It goes the entire thing decreasing, whereas tangent goes the entire thing increasing. And they also have different x-intercepts and asymptotes. So once I know the shape of the graph, if I just knew where the x-intercepts and the asymptotes were, then I pretty much could sketch this without even needing to plot points. And so the easy way to find the asymptotes and the x-intercepts are by thinking about the definition. If tangent is sine over cosine, anywhere the numerator is equal to 0, that entire fraction is going to equal 0. And remember, where it equals 0 is where you're going to have x-intercepts, right? So I could come up here and I could say, okay, where is sine equal to 0? Well, sine is equal to 0 at all the multiples of pi. 0 pi, 2 pi, negative 2 pi. All right? For my denominator, I could say anywhere the denominator is equal to 0, I'm going to have asymptotes, right? Because my function is undefined there. So in this case, my denominator is cosine. So I could say, I'm going to come over here and say, where is cosine equal to 0? And that's at all the multiples of pi over 2. So pi over 2, 3 pi over 2, 5 pi over 2, negative pi over 2, negative 3 pi over 2, and so on. So anywhere my numerator equals 0, I'll have x-intercepts. Anywhere my denominator equals 0, I'll have asymptotes. And sure enough, if I come over here, my numerator is equal to 0 at all the multiples of pi. And so sure enough, that's where my x-intercepts are. 0, pi, there'd be one down here at 2 pi, there's one over here at negative pi. Anywhere my denominator equals 0, I should have asymptotes, and this denominator is cosine, so cosine was equal to 0 at the multiples of pi over 2, and sure enough, that's where my asymptotes are, negative pi over 2, positive pi over 2, and 3 pi over 2. The cool thing is I get to use that same work that I've already done to help me with my cotangent, secant, and cosecant as well, because if I come over here and I look at cotangent, anywhere cosine equals 0 is where I'm going to have x-intercepts. So that's at all the multiples of pi over 2. So sure enough, at all the multiples of pi over 2 are my x-intercepts. And then anywhere my denominator of sine is equal to 0, I'm going to have asymptotes. So that's going to be at all the multiples of pi. And so, yep, right there, negative pi, 0, positive pi. There'd be another one over here at 2 pi. So if I just remember that the tangent function is increasing and the cotangent function is decreasing, with this little bit of work, I can get all the x-intercepts and the asymptotes for both of them, and then I know how to sketch those graphs. All right, very similarly down here with cosecant and secant, I could think about, okay, where sine is equal to 0, where my denominator equals 0, I'll have asymptotes. So that's at all the multiples of pi. And so again, you'll see asymptotes down here at 0, at pi, at 2 pi, at negative pi. And for secant, wherever cosine is equal to 0, I'm going to have asymptotes. That's at the multiples of pi over 2, so there are my asymptotes. So I can use that as a guide to help me figure out where those asymptotes are. But actually, we had found that the easiest way to graph the cosecant and secant graphs are to use their reciprocals. Like the reciprocal of cosecant is sine. So if I come in here and I draw the sine curve, now of course the sine curve is not part of the cosecant graph, but if I come in and I draw my sine curve, then I can just make the cosecant and secant graphs are kind of like a series of smiley faces and frowny faces. So like we've got the smile and then we've got the frown, same thing over here, frown, smile, frown. Notice that there's always like a neutral space in between -1 and +1 that's never used. The function only comes down to +1 and it only comes up to -1. I'm going to leave that empty space in the middle. So if I come in and I draw my sine curve, that just lets me know I'm going to draw cosecant so that it comes and touches the sine curve. So that would let me know, okay, I'm going to come down and touch here, I'm going to come up and touch here, I'm going to come up and touch here. So that lays out those frowny faces and smiley faces for me, and it would even lay out the asymptotes for me without me having to look at the denominator. Same story over here. If I come in and I draw my cosine curve, since it's the reciprocal of secant, then I could go through and say, okay, I'm going to make this come down and touch the top of the curve. I'm going to make this come up and touch the bottom of the curve, make this come up and touch the bottom of the curve, and that would lay that out for me as well. Okay, so those are our 6 basic graphs, and then we should be able to do the shifting and reflecting and stretching and shrinking and those types of things that we have learned with them as well. So here's our homework for tonight. On page A33, we're doing 77 through 82 all. And if you look on the homework exercises for those, there are none of those cute little graphing icons, meaning I shouldn't be doing these in my calculator. I should be able to do these by hand. And then your challenge is number 78. So even though it's in that assignment 77 to 82, it is still optional. That is your challenge problem. And then don't forget that we have our quiz over Appendix C2 and all of Appendix D, and don't need any calculator at all for that one.